Hi, my name is Andrea Vitrone. I'm in section M04 and this is lab 7. The purpose of this lab was to find the mass of a black hole being orbited by a star. To do that, I used two things: the momentum principle, which is the change of momentum equals net force times the change in time, where momentum and force are vectors. I just couldn't draw the arrow. And knowledge of curving motion, since you have to have a perpendicular force applied to the object in order to curve the object's path. So I broke down the momentum principle into dp dt equals F net. And dp dt can actually be broken down into a parallel change in momentum over time and a perpendicular change in momentum over time, and the same with net force. So it had parallel net force and perpendicular net force. And by setting those two equally to each other, I could find certain aspects of data that I needed in order to find the result, which is the mass predicted by the model correctly matched the result of Webbesign, or the mass of the black hole is 4.309 times 10 to the 31st kilogram. I ultimately found the mass of the black hole using the equation force equals g, which is 6 times 10 to the negative 11th, times mass of the star times mass of the black hole, which I solved for, divided by the magnitude of the position between them, the distance between them squared, which is right here, times the unit vector of the distance between them. And this equation right here is that equation just solving for the mass of the black hole instead of set equal to net force. When I ran my code to find the mass of the black hole, as you can see here, this is the motion of the star orbiting the black hole. I found that the mass of the black hole was 4.309 times 10 to the 31st kilograms, and that's the last line of the results. And when I checked on Webbesign for my answer, that turned out to be right, so it showed that my computer model correctly matched what was supposed to happen. So what does this all mean? Well, if you look at the arrows, the black arrow is the force perpendicular to the object in motion, and it points towards the center of the circle of curvature, allowing the motion of the star, which is our object, to curve. The blue one is the parallel force and is tangent to the object's path. The red one is the net force and is the sum of the perpendicular force and the parallel force. Now I'm going to show you what happens when you change net force to change in momentum over time, according to the momentum principle. So we're going to look at the perpendicular change in momentum over time, the parallel change in momentum over time, and the net change in momentum over time. So when I run my code, we can look at the arrows, and they look exactly the same as before. So the perpendicular change in momentum is the black one, which was originally the change in force that was perpendicular. The blue one is the parallel change in momentum over time, and the red is the sum of the two. So it is the net change in momentum over time, or the sum of the perpendicular and parallel components of momentum. The net force is the change in momentum over time, and we get this from the momentum principle. When you break them down into parallel and perpendicular components, as I did at the beginning of the presentation, you find that both, you can set the perpendicular change in momentum over time plus the parallel change in momentum over time equal to the components of net force. And you find that the parallel net force corresponds to the change in momentum over time in the parallel direction, and same with the perpendicular net force. The difference between the force components and the change in momentum over time components is in the calculations. Both yield the same numerical values, but the way to get there is different. So for force, you can do force equals mass times acceleration, and then you can find the parallel component of force using mass times the acceleration in the parallel direction, so the parallel component of acceleration. And this is equal to the parallel component of the change in momentum over time. However, this component can be calculated by doing the change in magnitude of momentum divided by time times the unit vector of momentum. So these two equations right here will end up with the same number, but the way they get there is different. Now what if a different black hole was put in the same location but with a different mass? Well, we don't know the mass, so the net force would be different depending on the mass. And if the mass was larger, then the net force would be greater, because the gravitational force, or the net force in this situation, is mass 1 times mass 2 times gravity. You get the picture. So if you increase the mass, you increase the force. which means a greater change in momentum and a smaller radius of curvature. Now, if a different black hole was put into this situation and the motion of the observed star did not change, there are two possible ways that this could happen. This could happen if the mass of the new black hole was the same as the original one, since the force of gravity is the only thing affecting the path of the star, or if the distance between the star and the new black hole was thus that the force of gravity would be the same as before. Alright, to conclude, I found the mass of the black hole using the components of change of momentum over time and net force, and I used the force of gravity and the momentum principle in order to do this. Thanks for watching!